Hello, everybody. Welcome in. Just going to give everybody a second to connect. Also, while I
Okay.
Yeah. Well, welcome to the Our Power, Our Planet webinar hosted by the Journal of Renewable and Sustainable Energy. My name is Nicaila Bryan, and I am the Journal Manager for JRSE. We are so excited to have you join us today. So I would like to introduce Professor Zhenhong Lin from the School of Future Technology of South China University of Technology and the Editor-in-Chief of JRSE. Professor Lin will be the moderator for today's webinar. Professor Lin?
Okay. Thank you, Nicola. Can you hear me? Yes. Okay, great. Well, hello, everyone. So exciting to have our three distinguished speakers with us. Um, I would like to first introduce the three speakers and briefly, and then we can start the presentation. Excuse me. Our first speaker is Dr. Michael Howland. He is Assistant Professor of Civil and Environmental Engineering at MIT. His group studies environmental fluid mechanics and the modeling, optimization, and control of renewable and efficient energy systems. His group uses synthetic approaches, including simulations, laboratory, and field experiments, and modeling to understand the operation of renewable energy systems, with the goal of improving the efficiency, predictability, and reliability of low-carbon energy generation. His paper, Evaluation of Wind Resource Uncertainty on Energy Production Estimates for Offshore Wind Farms, was the most read and cited paper in JRSE for the year of 2024. Please, let us welcome Dr. Howland.
Okay, great. Thanks for the introduction and happy to be here. So I'll go ahead and share my screen now. And before I launch into it, we'll make sure everything looks good. So hopefully screen is shared and it's full screen now.
Yes, perfect.
Okay, excellent. Great. Yeah, thanks for the invitation. Happy to be here and talk about our group's work and especially highlighting this paper, which was published in JRSE, which is a favorite journal of our lab. I'll skip the introduction of myself as it was already given, but I'll take the time to introduce the three members of our group who really led this work. That's Emily Condon, who actually started this project as a master's student, postdoc Carrie Clemmer, and I'll also touch on work of PhD student Ethan Shin's research in today's discussion. And so I'll get right into it and say that climate change and global warming represents an existential threat to human society. And one of the major opportunities to mitigate climate change and prevent it from worsening is in decarbonizing electricity generation through the use, especially of wind and solar technologies. And the opportunity to do so really comes from the fact that we've had a precipitous decline in the cost of energy associated with wind in blue and solar in orange over the last several decades. Here, the y-axis is showing the levelized power purchase agreement price, which is effectively a proxy for the cost of energy associated with these projects. Each individual project is shown by a circle. The size of the circle indicates the capacity of each individual project. And then the median trend line is shown by the solid line. What's really remarkable about this plot is overlaid on this curve is this dashed black line. That's the levelized cost of natural gas fuel. So essentially just the marginal cost of burning natural gas at existing natural gas plants, and this is in the US. However, we know we need to expand much more broadly to decarbonize, for example, in the United States, but also internationally. And an example of that kind of expansion is in offshore settings, where here in the United States and actually in Massachusetts specifically, not far from MIT, we're building the first utility scale offshore wind plant in the United States. It's called the Vineyard Wind Farm. And the estimated power purchase agreement price for that farm is $85 per megawatt hour. It's something like double or about 3 times perhaps the wholesale price in the electricity market. So we need to continue to drive down this cost curve for these innovative wind plants and increase reliability. And so what do I see as the key challenges and opportunities to really drive proliferation of renewables? One challenge, and a lot of what we'll discuss today focuses on this theme, that both the environmental system and energy system are predicted by uncertain computational models. So historically, as researchers and practitioners, we've thought about modeling environmental systems, think weather and climate models, in an isolated sense. So we're really interested in predicting weather and meteorology. And then separately, there's been a community of researchers who have focused on energy systems, so think power systems and dynamics. And increasingly through decarbonization, especially through renewable energy development, we are increasing the coupling between these two systems that we've historically studied in an isolated fashion. The second challenge and opportunity is that decarbonization requires a rapid technology scale up, and oftentimes this is pushing outside the bounds of existing models and data frameworks that we have today. So that increases the uncertainty in our projections that also affect our decision making. And the third challenge is that we require really rapid improvements in efficiency, predictability, and reliability for renewables to actually hit net zero. So how can we achieve some of these necessary innovations in renewable power? Other panelists will speak to other elements of this, including solar and storage. I'll focus on the wind power piece today. And historically, we've, in a simplified way, understood wind power production to be largely driven, of course, by the wind speed in the atmosphere that has a strong impact on the performance of individual turbines. However, increasingly, we're recognizing the fact that we're placing wind turbines in close proximity in wind farm configurations where individual turbines generate kinetic energy in momentum deficit regions called wakes that flow into downwind turbines and reduce the associated energy production of these downwind turbines within wind farms. And this is what it looks like in a wind farm modeling simulation that we can run from our lab group's methods. But this is also something that already happens at utility scale. So for example, this is an offshore wind farm, or sorry, an onshore wind farm we've studied for a number of years, where we can see the power production of this downwind turbine can be as much reduced as 50% of the power production of the upwind turbine. And that's actually in a separate study in JRSE. And it's worth mentioning here that the increasing scale of wind power results in taller turbines, which are typically accessing winds higher in the atmosphere that generally have lower turbulence. And we're also moving wind farms offshore, which also has lower ambient turbulence in the atmosphere. You may think lower ambient turbulence is a good thing. If you've ridden on planes before, you don't want turbulence, generally speaking. But actually, turbulence acts to mix out these kinetic energy deficit wake regions. So if we have lower ambient turbulence, that generally means that the wake interactions will be higher. The other challenge is that we're increasing the rotor diameter of wind turbines very rapidly, and that increases the size of these wakes and therefore likely increases the magnitude of these wake interactions. Putting all of this together, wake effects are predicted to reduce the energy production of future offshore wind farms that we're building here in the United States by up to 30%. Okay, so we're really interested in addressing this challenge and really thinking about this inherently challenging problem that converting the kinetic energy of the atmosphere is fundamentally multi-scale, going from the individual boundary layers on wind turbine blades to the wind turbine rotor to wakes to even neighboring wind farms interacting with each other. And that's all in the context of the fact that these wind turbines and wind farms are operating in the multi-scale atmosphere itself, which is already a challenging modeling endeavor. So the question we wanted to answer in this particular study published in JRSE last year is how can we model offshore wind power production, and especially to have a sense of its uncertainty? How can we quantify the uncertainty associated with a wind plant before we actually build that wind plant? So getting into a little bit of background on atmospheric flow at a very high level, we want to think about how we can model atmospheric flow across scales for decision making, especially in wind power. design and operation. So at the global scale, we can think about setting up something called a climate model. That's also called a general circulation model or an Earth system model, which requires essentially gridding the entire Earth. So you have to have computational grid points across the entire Earth to solve together for the overall flow dynamics across the planet. However, because of the need to grid the entire Earth, we have essentially large spacing between each grid point that's limited by the computational complexity of that problem. And so from grid point to grid point is something like 100 kilometers. So it's very coarse. We can zoom in one level further and think about a mesoscale model, often called a weather model or numerical weather prediction, sometimes also called regional climate modeling. And now, because we're only constraining our domain to a smaller region, we can have a finer resolution, usually down to 1 kilometer or more often, perhaps around 10 kilometers in resolution. One level finer, then we start to think about microscale flow physics, and that's really getting into the realm of computational fluid dynamics, where we can start to actually resolve that turbulence and feel more confident in our predictions by parameterizing less of the processes. But again, returning back to this environmental system picture, these natural and engineered systems that we're building, such as wind power, exist in the atmospheric boundary layer, which is the lowest region of Earth's atmosphere that's dominated by chaotic and turbulent dynamics. And it's really influenced by small scales. And so the fate of weather, climate, and extreme events really depends on small scale processes that are largely unresolved in weather models. And so we want to essentially understand how this kind of uncertainty, the degree to which we're not resolving key processes in the atmosphere, how does that affect offshore wind power production estimates before we build that wind farm? And really, this is going to zoom in on that middle block here, where we're going to think about essentially what is the underlying uncertainty of these mesoscale weather models. So this is our region that we wanted to study this. This is, again, that first utility scale offshore wind farm here in New England. So that's Martha's Vineyard, Cape Cod, and then Boston and MIT are somewhere up here, not shown on the map. And so this is, this is that first utility scale offshore wind farm we're building here in the United States, and we're modeling it as 62 IEA reference 15 megawatt turbines, which is matched to the spacing of that actual offshore wind plant in terms of rotor diameters. And we have a fundamental challenge when we start to build these offshore wind plants, which I mentioned on the introductory slides, that we're moving into regimes where we either lack data or we're moving outside the bounds of where we've relied on models in the past. And especially in the offshore wind setting, we really lack in situ, so actually in environment sensors that are used to measure what the wind patterns will be where these future offshore wind farms will operate. And that's because building in situ sensors in this far offshore environment is really, really expensive and also practically very difficult. If you want to build a meteorological tower, for example, anchoring it to the sea floor, 15 miles offshore is a challenging task. And so instead, we use wind resource estimates that are either driven by numerical weather prediction, which has a benefit of very high spatial coverage, as I mentioned on the previous slide, but oftentimes is quite limited in temporal extent because we have to run these models on supercomputers, so we can't simulate thousands of potential years. And it's also limited by modeling error and uncertainty that's inherent to these numerical weather models. On the other side, we have limited in situ measurements that are highly limited in spatial coverage. So we might have one or two near a certain lease area, and that could be either direct in situ measurements like a sonic anemometer that's measuring wind speed, or it could be something like a newer technology called floating LiDAR, where we put a LiDAR on top of a floating buoy, essentially. And the benefit of these measurements is that they have no or limited modeling error and uncertainty, but again, they're sort of limited in extent. One reason we selected this site is that there's actually a long-term mounted LiDAR that's not floating, that's been collected by the Woods Hole Oceanographic Institute, and that's been collected over a number of years, and we can use that as essentially a high-quality reference. So essentially what we wanted to do in this study is evaluate wind resource at this particular site and drive a wind energy model at this offshore wind farm using these three estimates of wind production. We can use the in situ measurements that are taken at this Woods Hole Oceanographic Institute, Martha's Vineyard Coastal Observatory, which is about 15 miles north of this Vineyard wind farm, and that's taken with a wind LiDAR. Then we can also use weather modeling at that same site where we have the in situ measurements. And by comparing these two estimates, we essentially quantify modeling error and uncertainty that's inherent to that numerical weather prediction model. Then, using the weather model, we can go and directly probe what the wind resource is at the actual site that we're going to build. And by comparing the weather model estimates between the place that we have an in-situ sensor and the actual wind farm site, we essentially quantify the error and uncertainty associated with the fact that we usually don't have measurements directly at the actual wind plant that we're going to build. And so that's the benefit of these three data sources. Just at a high level, qualitatively, from the different sensors and measurements and also model predictions, we can take a look at one of the main differences, so cutting through a lot of the noise in the data, essentially, and a lot of details in the paper. One of the main differences we saw is the difference in turbulence predicted by each of these estimates. And so here I'm showing a contour as a function of month and height for the turbulence intensity, which again is going to dictate that wake recovery. These are from the in-situ measurements at this site that's 15 miles north of where we're building that offshore wind farm. And here are the weather predictions in the middle column at the same site as the sensor. And so we can see the difference between these two is essentially driven by modeling error and uncertainty. And then by comparing the middle column to the right-hand column, that's differences associated with the location at which we're measuring the wind resource. And the high-level story is essentially there are differences between all three of these estimates, especially in the degree to which the wind turbulence is predicted as monotonically decreasing in the weather model, which is not exactly what we see in the in-situ observations. So getting into more details on the power production estimates, how this impacts the sort of final decision-making that we care about in this wind plant application, we can look at the annual energy production of this offshore wind farm by looking at a few candidate hub heights that we could build the turbines. And we're really interested in understanding how this uncertainty actually depends on height, because the reliability of our weather models does depend on what height we measure in the turbulent atmospheric boundary layer. And so the mean estimates are shown by the dots. The error bars show differences relative to two different models. So essentially the in-situ measurements versus the numerical weather prediction, that's shown as an error bar. And then the shaded region shows interannual variability, which is basically how much the wind resource varies from year to year and gives us a sense of the uncertainty inherent to the natural system. And what we could see is that the uncertainty associated with how we estimate the wind resource is actually larger than interannual variability, meaning it's statistically significant at lower heights in the atmospheric boundary layer. And then it tends to decrease as we go higher aloft. This is kind of an interesting trend, because if we really zoom in on the wakes by calculating something called farm efficiency, so that kind of removes everything but the wind turbine wakes, then we can actually see that the uncertainty tends to increase. So this is really that zooming in on the fact that the turbulence estimates are different between these different resource assessment technologies. So we can see statistically significant differences in AP and efficiency that stem from this data source uncertainty, depending on height in the atmospheric boundary layer. And I'll just finish with a last essentially slide to say we're also pushing a little bit more on this idea of how we think more generally of quantifying uncertainty in numerical weather models and thinking about how this impacts renewable energy more broadly. And so returning back to this picture, we essentially want to think about how do we quantify uncertainty in computational Earth system models in a more general perspective, rather than just forward propagating different estimates through a model of a wind farm. And to do that, we're leveraging the fact that we can run high fidelity turbulence and convection capturing simulations using scale resolving technologies like large eddy simulation. And then we can use those data to quantify modeling uncertainty. But a primary bottleneck is basically that quantifying uncertainty requires many, many evaluations of the weather model we care about. And so what we're developing as a lab group is essentially a data-informed physics-based approach where we combine machine learning accelerated inverse uncertainty quantification with these turbulence capturing small scale dynamics. And I'll skip through the details here. They're in this paper about the open source software if you're interested here. But we basically speed up the inverse uncertainty quantification process using a judicious combination of optimization, machine learning, and then to calculate the uncertainty of the underlying computational weather model. So this is where we're going, and we hope that this is a nice follow-up to our JRSE paper here. And I'll end here. And I don't know if we have any time for questions, maybe briefly. I went slightly long, but yeah, excited to be here. Thank you.
Excellent. Dr. Holland, thank you so much for this very interesting talk. Nikela, do you want to go with Q&A or hold it until the end of the three talks?
Yes, we can invite in a question or two if there is in the audience. You can put it in the chat. If not, then we can move on.
Okay, any question from the chat room right now? No, I actually have some questions. I will maybe ask one or two. Uh, sorry, hold on a second. Dr. Holland, thank you. I learned something. I think quite interesting here. So I see that the estimation error decrease with the height. So and that is based on your comparison with the simulation result, right? But how do you explain that? Is there a is it because it is away from the service and the service tend to like affect the flow and make it difficult or what?
Yep.
So do you have like a physics based?
Yep. Yeah, it's a really good question. Yes, essentially you summarized it reasonably well. Uh-oh. Looks like he maybe dropped off, so I'm not sure he can catch the answer in the recording. Oh, there he is. Okay.
Oh, okay.
So yeah, it's a good question, and you summarized it well actually, is that basically what we're trying to show here by comparing two different metrics is actually a competing effect of uncertainty. So annual energy production is largely driven by wind speed. And so the fact that that uncertainty decreases as a function of height tells us that we are getting more and more confident in our estimate of the wind speed. This was somewhat of an expected result because as we get further away from the ground, we get closer to essentially the free atmosphere, which is not so much influenced by turbulence, and we are less sensitive to how we parameterize turbulence in the atmospheric ground layer, which is that lowest region of Earth's atmosphere. That's really dominated by turbulence and the interaction with the surface. Now, this was a more surprising result actually for us, where the farm efficiency uncertainty increased as a function of height. And it was really driven by the fact that we had somewhat notable differences in the turbulence itself predicted as a function of height. And so farm efficiency is a metric that's really dominated more by the second order kind of variables of the atmosphere, like turbulence. It basically normalizes out the dominant effect of the wind speed. And so this tells us that we need to continue to innovate on methods to reliably predict these second order statistics like turbulence in the atmosphere through better parameterizations.
Great. Just to have a quick follow-up question on that is that on the y-axis, the unit is GWH, so it's energy, right?
Exactly. Yeah, this one is annual energy production. So that would be essentially the energy production of the wind farm, of the total wind farm integrated over the entire year. Exactly.
What if you measure the what you change it to a power, real-time power, or even daily power? Would that
Yeah.
make it even more difficult in terms of the error? Yeah.
Yeah, it's a good question. So this farm efficiency is almost doing that. What this farm efficiency is doing is it says, okay, at every instance in time, because that's actually how we calculate this AEP,
Yeah.
is we take power as a function of time and then we integrate it. This farm efficiency basically takes that power as a function of time and then normalizes it by what the farm would be if there were no wake effects. So if you had basically the same number of turbines, but they were all operating independently from each other and had no wake interactions. And so in that way, it normalizes out the background wind speed, which tends to dominate these sort of mean energy metrics. And so that's why this one is really highlighting essentially the wake losses, which is challenging to predict and largely depends on the turbulence in the atmosphere.
Okay, thank you so much for answering my question. Any other questions? So, Nikayla, what's the time allocation? We have a total of 1 hour. Is that right?
Yes. So if anybody has any questions for Dr. Highland, please put it in the Q&A and he'll be able to see it and answer them as we continue.
Right.
Yeah.
Excellent. Okay. Thank you, Dr. Holland. So next, I'm happy to introduce Dr. Gerardo Diaz. He is deputy editor with JRSE and joined the mechanical engineering program at University of California, Merced in 2005 as a founding member of the faculty. He is currently the director of the Sustainable Plasma Gasification Lab and was co-director of the UC Solar Institute until 2019. Professor Diaz's research now focuses on the sustainable conversion and application of renewable energy resources, in which work includes the study of the material properties and the applications of biochar and activated carbon as circular economy materials for greenhouse gas emission reduction, soil amendment, solar desalination, wastewater treatment plant streams, and the construction industry. Let's welcome Professor Diaz.
All right, can you hear me?
Yes.
Okay, perfect. Yeah, thank you, St. John, for the introduction. Let me go back here to my presentation. So very happy to be here. Thank you for the invitation. Yes, as St. John was saying, I've been associated with the JRSE journal for probably about 4 years now or something like that. So this is a work that we did some years ago. It has a background on some of the events or effects that have been happening in California on the utilization of natural gas. And what we wanted to look at was basically, there's always studies of performance, which technology works better, things like that. But what we wanted to do a little bit more was to see what is the location where some of these technologies would make sense to implement, and where are the locations where you shouldn't really probably implement some of these things. So again, in the concept of renewable energy, my group, as you heard the introduction, we work in different conversions, biomass, but also solar, specifically solar thermal, type of conversion. So we wanted to look at this technology that is called mini channel solar collectors, and use satellite-derived data to be able to analyze the performance and see in what locations should we install them. So a little bit of the background here is that natural gas for residential water heating, it's actually still being consumed quite a bit. As you know, we're trying to go away from anything that is fossil fuels. So in fact, in California, they have banned the sale of natural gas type of water heaters starting in 2030. So slowly that's going to be decreasing. So we have to look at other technologies. There's certainly a lot of technologies out there, heat pumps and solar collectors are one of them. But why do we look at this aspect of water heating? Is because it has a substantial fraction of the consumption of energy in households. So it's about 60%. So again, one of the ideas is to target the sectors or the fractions of consumption that are the most important ones. You can see how space heating is also very important. So again, what triggered some of this analysis? And partly it's because, again, if you look at some of the natural gas related incidents, these are leaks or even explosions or things like that. I mean, when you look at California, there's actually, historically, there's been actually quite a few incidents. In particular, the incident that triggers some of these projects, this project in particular, and a follow-up that we did later on, was the Aliso Canyon gas leak, where you can see here some sort of infrared type of a picture where you can see the leak. And this was going on for months, and you can see that there were tons of methane that were released to the atmosphere. Of course, when we're trying to reduce the effects of climate change, we really don't want to be releasing methane to the atmosphere. So in that sense, we looked at, okay, if we were to look at other technologies where they can help to reduce the consumption of natural gas, and eventually we can start phasing out that technology. The other thing that is very important to consider is the fact that we are going into an electrical electrified type of economy, where we're trying to move pretty much everything to operate with electricity. But again, there's limits. So we have to look what we call the roof real estate. If you look at the installations of solar panels in general, we're talking about relatively small installations. Many of them might be covered by the shade of trees or any sort of buildings and things like that. So even though we might have a large installation like this one, it's not that effective. So and what's the other alternative to basically just purchase electricity from the utilities, which again, if they increase the rates, then it gets to a point at which electricity becomes very expensive. So so again, when you look at, for instance, the real estate in a roof that is used by a solar collector. You can see, for instance, here, these are thermal solar collectors. Independent, these are evacuated tubes, but you can also have flat plates or other type of collectors. They use a really small amount of the space on the roof compared to what you would need for a house that has a large consumption. So, and again, when you start looking at, we're putting electricity for electric cars. So if you look at the consumption, say 7 to 11.5 kilowatts, and if you multiply that by the number of hours that the charger is operating, say 7 hours or 8 hours, if you're not in a supercharger, then pretty much the whole output of your solar panels is taken by other applications that might have higher priority than, say, heating water. So, and again, when you start looking at central conditioning, for instance, where we live here in Merced, we have temperatures of 40 degrees. So it becomes essential to be able to run your air conditioning. It's not a matter of, well, yeah, we're just going to make sure that we have a comfortable type of condition inside the house. No, if you don't have air conditioning, it can be very dangerous for especially young kids or older people. So again, we were looking at technologies that would use somewhat of a very small amount of power and be able to have reduce in a certain way the consumption of natural gas, and also in a certain way be able to take a large part of the load of heating water. So here we've been working with these mini channel solar collectors, and the whole idea is in a certain way this one. When you look at the regular flat plate collector, usually there's a flat plate like the name says, and it's very thin. And the point of contact with the tubes where you have the water flowing is usually just here by, I don't know, you have different sorts of soldering or ultrasonic welding or things like that. So the point is very, the point of contact is very small. So there's a large resistance for the heat to be able to go, the energy going to go from the middle of the plate, for instance, here to there. So we came up years ago with the mini channel collector, which again, these are technologies that have been used significantly in automotive industry, in air conditioning industry, and things like that, where you just have a tube where you have these mini channels here, and then the solar energy goes there, and you pretty much have just the wall here as your resistance. If you have never seen a mini channel, these are very little mini ports, but then again, they're very efficient. So their main feature is that they're more efficient than the flat plates. And again, if you compare them to, say, vacuum collectors, you don't have to really deal with the loss of vacuums that it's typical in some of those collectors. So what we did a demonstration project. We have a much larger demonstration also at a apartment complex, which again, that's going to be a follow-up type of paper. But if you just look at the household here, we have the collectors, and we have a tank, and we have usually, if you're not able to meet the demand, there's going to be an auxiliary type of heater, which again, this could be electric too, so that you could completely eliminate the use of electricity. But here we had a tankless natural gas-fired water heater. And what we did was we looked at certain locations. So we installed that system in Northridge, Southern California. And we needed to obtain weather data from that. So there's a station, Station 219 weather station, where we are collecting that that weather, but also we wanted to look at information from other weather stations. So we looked at one with a very different type of weather at Davis, UC Davis there. And the whole point, the idea was to be able to somehow predict the performance of a system like this anywhere here in California. The problem was that there's not enough resolution of these weather stations everywhere in the state. So we said, well, if we can't really have ground data for all the locations in California, we could use satellite data. And in that way, we have to validate that the satellite data matches the ground stations. And then from there, we can actually look at the performance of the collector. So we use different databases. We use CIMIS for ground data for the weather, and also we use NREL SAM model for modeling, because we're not just modeling the collector, we're modeling also the piping and the tank and everything. So we did that. But also once we had validated between CIMIS and the data here from the satellite, we were able to basically use a large number of points where we could actually predict the performance of our collector. So that by having a 15 kilometer by 15 kilometer kind of grid all over the state, we were able to look at roughly a little bit below 2,000 nodes for the entire state and analyze the performance in that place. So again, first of all, we looked at different databases. We have CIMS here with SIMS. All of them have their acronyms. And the idea was to basically look how the ground-based data that we were collecting at these environmental stations would match the satellite data that we were collecting. And you can see that in general, it does very well. But the problem with SIM is that it's not located. We couldn't get the information all over California. So we ended up using a different database here. And again, the idea was to look at how it would be able to predict certain parameters or certain aspects of the solar water heater system. So we looked at storage tank temperature as a very good indicator, because again, depending on if you're using water or you're having to replace that water with what's coming from the tap before it gets heated, then the tank temperature gives you a good indication. So here again, we had for instance, 2020, year 2020, and we're looking at roughly looking at the data from CIMIS, how that system operates. It's almost the same as the satellite data here that we have there. And we also looked at 2022, and we could see that the results were very comparable. So in a certain way, we could use satellite data to analyze our system and have a great confidence that the numbers correlate very well with ground data that could be obtained from weather stations. So again, when you look at some of the information that we were interested in order to be able to feed to our model. So with our model, we have a model that was designed here at UC Merced for predicting the performance of these mini channel collectors, and we coupled that model. That model is done in engineering equation solver. And we coupled that model with SAM, which is from NREL, which allows you to somehow analyze the entire system with piping and tank temperatures and things like that. So we were looking at some of the information collected from the weather data, where again, global horizontal irradiation, direct normal irradiation, and we can see that there's a significant difference of those parameters here in California. Also, if you look at actual temperature, average temperature here in the States, you can see here, we are located here in the middle of the Central Valley, but you can see how Southern California has a large average temperatures. And as you start going to the north, then the parameters change significantly. So all this was taken into account in the model to be able to run this for a substantial length of the year, pretty much the entire year, and then from there make decisions where should we install some of these systems. So again, some of the parameters that we were calculating, for instance, solar fractions, things like that. Solar fractions are is basically the fraction of the load that is taken by the solar collector. So we're looking at, again, since we had an auxiliary system about in certain locations of the state, you can actually have pretty much half of the load taken by the collectors. Notice that in winter, you're going to have less performance. So in winters, usually where you have to have some sort of auxiliary unit helping to bring up the temperature, depending on the temperature you want. If you're already obtaining, say, 40 degrees C from the collectors, then that's probably enough not to have any sort of auxiliary system. And again, we're looking at the tank temperature, and you can see that there's a significant variation of tank temperature along the entire state. So where should we locate these systems? Again, it's we did a k-means clustering type of analysis in which we collected all the data, and we're basically trying to find what are locations that somehow have parameters that are similar so that you can consider them as some sort of a cluster. When we look at that, you can see that there's certain clusters that were formed. In this case, we found 5 clusters were in a certain way representing the data in a very good way. So we were looking at average tank temperature, and here we have the average solar fraction. The dots here are the standard deviation. So you can see that there's some areas, especially where you have less abundance of solar resource, the standard deviation was very high. So some of these locations maybe didn't make a lot of sense to have some of those systems. But then you have other areas where you have a smaller type of standard deviations, but you have a fairly good value of the parameters we were interested in. So when you plot these things, you can see roughly that these clusters are kind of scattered all over California, but there's certain areas that are localized here, and you can see how these clusters start evolving in a certain way. So we said, okay, so one thing is the performance of the system, but also it's important to see where the population is located, because at the end of the day, you want to make sure that this is utilized in areas, especially in dense areas, where that's where solar collectors shine because of the capacity of being able to heat up water very quickly. In the sense of you can have a, I don't know, 80-gallon 300-liter type of tank, and it could be basically reach the operational temperature very quickly in especially in dense areas where you have large populations that are going to consume a lot of hot water. So, so again, when you look at California, you can see that a lot of the population is going to be, say, here in Southern California, the Bay Area, maybe a little bit here. You have the Central Valley, but there's areas that actually showed very well in terms of the clusters that there's very low density of population, especially here also in the north, where you have a lot of forests and things like that. Not only you have a low value of the parameters, but also you have low population. So you start looking at locations that maybe in this area makes a lot of sense to install some of these collectors. And this could be done for different technologies. The idea in a certain way wasn't to look so much at the performance, but also how do we generate a methodology to be able to decide where to install certain technologies. The other parameter that was looked at is the consumption of natural gas. Where are we consuming, doing the large consumption of this natural gas resource, which again is a fossil fuel, so we're trying to phase out that. And you can see, again, Southern California and certain areas in the Central Valley, the Bay Area here, depending on the city, you can see some cities are really, really consuming a large amount of natural gas. And then you start seeing other counties where, again, it's less of the consumption. So when you're trying to cause an impact in terms of climate change, you probably want to target the areas where you're having very, very large consumption of this resource. So again, just to keep it short, some of the conclusions are the mini channel technology was able to significantly reduce the consumption of natural gas. Again, if you pair it with some sort of you could even pair it with a heat pipe, with a heat pump, but you could also have just an electric type of heater, and you could completely remove the electricity. I mean the natural gas consumption. But anyway, if you're still using natural gas as an auxiliary system, you could reduce pretty much half of the consumption. And then again, we looked at interesting things. COVID showed that there was a less consumption. So even though people were more at home, but they consumed less hot water. So you can see the effect of COVID there. And when you look at the clusters, you can see that Southern California and Central Valley are two places where it makes a lot of sense because of the solar resource, but also the consumption that you have and the population in the area. So yeah, so I don't want to take more time than this. So yeah, thanks for listening.
Okay. Well, thank you, Dr. Diaz. So this is looking at how the solar energy-based water heating the technology can reduce the natural gas consumption, right?
Yeah.
For the function of water heating, right?
Yes.
Yeah. And you also did a great job of quantifying for the case study of California, and yeah, looking at the whole state and looking at the variation of the solar energy across the state, right? Yeah.
Yes, that's it. Yes.
Cool, cool.
And again, the main part was to be able to have the information of the weather pattern and things like that, so that we could actually have a very high resolution grid, so that we could analyze the performance all over the state. Something that we couldn't do with the weather stations that are ground-based because there's not that many of them.
Okay. And do you also maybe you are already doing that to quantify the cost benefit of the technology, and what is the number looking like?
Yeah, these systems usually, I mean, if you install them, again, you have probably $8,000 or something like that, but it's going to be depending on the reduction in the consumption that of either electricity or natural gas that you're going to have. So there again, the payoff time. There's an interesting aspect that when this Aliso Canyon happened, there was a rebate for putting the system, and the rebate it was used completely. So in that sense, people start saving money from the very beginning. Now, if you don't have that, it might take you some years to pay it off, but at the end of the day, these things last, I don't know, 25 years or things like that. So you're going to be better off installing some of these systems, whether it's again a heat pump or a system like this. At the end, the idea is to reduce natural gas consumption, and in general, these technologies tend to save money to whoever installs them.
Excellent, excellent. Any other questions from other speaker or from the chat room? Okay. If anyone have any continue to put into the chat room, and if we have time at the end, we can have the speaker answer too. Okay. Thank you again, Dr. Diaz, for the excellent presentation. Thank you so much. So last but not the least, we have Dr. Haobo Dong. Dr. Dong is a associate editor with JRSE and is a assistant professor at South China University of Technology. He has long been engaged in energy storage technology and battery health monitoring research. He has led or participated in multiple research projects funded by the UK Engineering and Physical Sciences Research Council on next-generation energy storage batteries and battery monitoring technologies. His research group explored the integration of energy storage technology with the low-altitude economy, including efficient energy management and distribution models for aviation and drone application. With that, let's welcome Dr. Dong for the presentation. So just to add that we have wind energy, we have solar energy, but both are with high uncertainty. So we need energy storage. So it's a perfect mix tonight.
Yeah, thanks, Professor Ling, and thanks for the introduction. Yeah, it's my honor to be here and to present the work that we have done. With Professor Ling and to share the things in the JRSE. So for today's class, I will show the kind of the recent work that we have done for the battery. So I will discuss what's next for the battery, and we will try to focusing on some like the technical breakthrough that need to like drive the decarbonization in transportation and also the great applications. So like as we know, as well as like accelerate efforts to the decarbonization sector like the transportation and also the great application, the kind of the demand for the advanced kind of the energy storage system is more like crucial than ever. And the things is because of the transportation electrification, such as we use to like replace the ICE vehicles by the EVs, and also something which is kind of the important the key drivers, but also it's also like the essential work that we have to do to try to stabilize some renewable energies such as the solar and the wind power. So it's kind of the essential part to use the and the kind of the advancement kind of the battery technologies to store the power that we could be used by the solar and wind. And here is like the history of the battery. Back to the 18th centuries, we start with the water pipe battery, but now we have all the different types of the battery, such as the lithium battery, and now we like also start something like the manganese ion battery and the potassium ion battery and also the sodium ion battery, and etc. So for like today's talk, we will like focusing on the all the techniques that we should be focused for the future. So try to meet our like climate change goal by the 2050. As you can see on the right hand side, we had so many different types of the energy storage. Like apart from the electrochemical types, we also have some mechanical type of the energy storage, such as the flying wheels and also something like the compressed air. But all the different types, the energy storage has the different energy density and also power density. So we have to choose something like the best suit one for the different kind of the scenarios. But in terms of today's like the current challenge, we mainly focus on the lithium battery. So like as you may know, we try to shift to the high energy density with the more like safeties and lower cost base. So we try to face the challenge like the solid state battery and something like the sodium battery and also the lithium sulfate battery. So like as we taught in last page, there's kind of so many different types of batteries. And so like what's the technology that we normally use or like will be used to like beyond the lithium battery, since we all know the limitation of the lithium battery. and such as it has the cost variation, and also like it has the limited the energy density, which is like less than 350 watts per kilogram. So to try to increase the energy density and the power density, or something like the cost effective alternatives, we normally use the different for like different types of the battery technologies. First one is sodium-ion battery, which is like focusing on the kind of safe battery, and also the second one is solid-state battery, so which is aimed at the high energy density to greater than the 600 watts the 600 watts per kilogram, and also for the lithium sulfur battery, so which is a really high the energy density in the theoretical calculation, and so which is also a type of the solid state battery. And the fourth one is the multivalent metal ion battery, which is mainly like designed for the stationary energy storage. So the right figure is something plot that we named as the Repner plot. So the y kind of axis is the energy density, and the x-axis is the power density. So as you can see, like the current line is based on the different time for the different kind of the energy storage. So when we choose to use different type of the battery, we have to like focus based on this kind of Repner plot. The first part is we try to rethink the kind of battery that we need to use in the kind of the transportation. So we all may know based on the different data, the different kind of data, there is kind of the undergoing quite increase in the electric vehicles, so which is growing kind of rapidly, and also there's quite like interesting point is the PHEV, something named as the plug-in hybrid electric vehicles, is also bridge gap between the combustion engines and also the kind of the electric vehicles. So in China, it's like 1.5 million units increase in the PHEV instead of the other types of the kind of the electric vehicles. And the third point is there also kind of the increased trend in the micro kind of the micro electric vehicles, which are based on to the short range, which is normally like less than 200 kilometers for the usable range. So based on this, we can see the different types of the electric vehicles use different types of battery. Some of them use the LFP batteries, and for the short type of range. For the long range, they normally use the nickel cobalt batteries, which is also a type of the kind of the lithium battery that we normally use. But if we try to like increase the range for the electric vehicles, people for the next steps, people normally try to use the solid state battery to increase the range. So this is why we need to focus on the different types of battery and see what is trained to be used in the electric vehicles. And in terms of the transportation, we also have something like the urban rail systems that we normally be kind of neglected in our discussion. So for the rail like transportation, we can use the energy storage to like empower something from the brake restoration. so we can save the energy when the rail or the subway to do the brake or during the brake. And so like normally we like in industry, so people normally use the supercapacitors or the flying wheels to store this kind of energy, since this energy is in the high power density. But the things like in the reality, the outcome is not it's not that perfect. So we think we should pay more attention to the rail system. So if we can use all the power or some space like underneath Earth, so we could to apply something like the advanced like more safe energy kind of battery to save energy from the urban rail system. And the kind of the next the transportation that we will into focus is the air transportation. The thing is in the air transportation, the kind of challenge is like even more to be pronounced. Something like the electric aircraft is really famous in the China right now. But this type of the vehicles should need to have the high energy density and also have the power to weight ratio. So we should need to be like really take care of. But currently there's not like so like currently the lithium battery are used in the electric aircraft is not that sufficient to support the large scale to have the large range. So in this type of the application, we normally should focus on the solid state battery or something even like the hydrogen battery to have the higher energy density and to also increase the battery safety. And the last one in the transportation is the kind of the marine transportation. But this as you can see from the figure, there's no too much research in this area. I just summarized all the type of the electric kind of marine that we used like right now. But as you can see, most of them are based on the lithium battery, so which is in the short range, and some of them use a flow battery, which has the like much larger like energy storage, but there's no like the one that we could make the common agreement in this area. So like apart from the transportation, we have the other kind of sector that we should be mentioned, so which is the grid application. So normally people use the lithium battery for the grid application, but as you can see, there's like too much safety issue that we should consider. And so in order to increase like the independent application, we have to like focus on kind of the new kind of technology, such as the aqueous ion battery to increase safety, and also we could use a flow battery to have the long-term energy storage. And also there's one kind of interesting point in the grid application. The one is the vehicle to grid. Since we have the type of the tremendous increase in the electric vehicles, so we can use them as like a power bank to apply the power back to the grid, and also the kind of users could use this kind of mechanism to like trace the kind of power that they should be stored in the EVs and to sell the type of the electricity back to the grid. And this is like really kind of new kind of market that we should pay more attention on it. And in terms of the grid application, since we have too much different like different conditions and also different kind of the scenarios, so one single like batteries cannot satisfy all the requirements. So it is quite important to do the hybrid energy system. So like for example, we could use a lithium battery to provide a long-term energy storage and use the supercapacitor or something like the flying wheels to provide the power for the like more like the frequent charging and also the kind of the discharging behaviors. And also we could use some like advanced technology such as the things like the vanadium flow cell and also the zinc battery to have more like the cheap and the long-term the energy storage. So in terms of the conclusion, so like this way we try to like provide the concept that in the different area, so based on the battery technologies and also based on the things and also policy that we found for the different countries. So that's all for my present today, and thanks for listening.
Great. Okay, great. Thank you, Dr. Dong. I think this is a very important topic. And for one thing, as you described very well, is the different application require different attributes of the storage technology, and it's very complicated to differentiate and to decide and quantify the required performance for different technology and different application. And they also, because right now people are talking about solid state and next generation. And one thing you can look at the energy density, the safety, performance, and you can say a lot of good things about solid state. But another thing is that it's very difficult to manufacture. The way to manufacture solid state battery is very different from the current lithium-ion technology, and that comes with a cost, right? So, what do you think the difficulty or the cost to produce a solid state battery, even when the technology become mature? What do you think of that?
Yeah. So like yes. Like to be honest, it's quite like difficult question to be answered. Things for solid state battery, I think by like 2027, some of the companies such as the ATL, they have mentioned that they will like have the solid state battery which can be commercialized. But I think this can be like only done by the big company. For the some of the researchers, we should like focus on the kind of the material and also the mechanics in the back of them. But for the commercialized, I think by the 2030s will be the ideal time. Yeah.
Okay, thank you. And I also recently heard that the what's the name of neither star again? Sorry.
ATL, yeah.
ATL. They have
Yeah.
announced Sorry, I forgot the name. What was
Yeah,
it?
the CATLs like also announced the sodium, right? Like
Yeah,
a sodium ion battery.
sodium ion battery and for even for vehicles, right?
Yeah,
Yeah.
even for the
Okay.
vehicle.
Yeah.
Yeah, for the short range vehicles. Yeah.
Right. That's exciting. Yeah. Do we have any other question from the chat room or from other speakers for? No?
Nothing from the chat room, but as I put in the chat, if you guys have any questions that you think about after today's session, please email us. I left the journal manager email in the chat, and I will coordinate with the panelists to get your answer.
Okay. Is the video is going to be on YouTube?
We will share the video and a link
Okay.
afterwards, yes.
Okay. Okay. With that, do we have any other last comment from any speakers? Anyone? Okay.
Just thanks for hosting.
All right.
Yes.
Thank you all. Yeah, excellent. Okay, so thank you all speakers and thank you, Nikila, for organizing this event. Let's conclude here and have a good day or have a good night.
Yes.
Take care. Bye-bye.
Bye,
Thanks.
everybody.
Thanks.
All right, take care.
Oh,